Now let's look at the final section for the discussion on premixed blending. We try to give you some basic understanding about the turbulent premixed friend. In our previous lectures, we described the detail about the combustion characteristic of laminar premixed friends, including the friend temperature, friend speed, and friend instability, and also the Lewis number coupled with the flow stretch effect. And I hope those kinds of basic concepts will help you to understand the combustion behavior, combustion characteristic of a laminar premixed frame. But in reality, in many different kinds of application, the flow field should be the turbulent. In turbulent case, let's look at how the turbulent ADs change the frame structures. People should know the basic structure for turbulent flow is a lot of AD, right? AD means that they have a small vortex, okay? And the vortex has their own dimension. Therefore, people try to analyze the turbulent structure based on the size of the AD. Look at this plot. Those materials you can go back to follow the page 1.33 in our slides, or you can follow the PowerPoint file last time I gave you. And you can, I think I use the PowerPoints is better because I bring these two important figures together, including some descriptions. Okay, look at the figures shown in the left-hand side. The top four plot show you there is the scale, right? When you look at the horizontal axis, there is a 0 and LH, eta, and L. 0 means the dimension is 0, and LH represents the frame thickness. Okay. Now eta means the chromograph scale, defined by nu to the power third divided by epsilon, and quarter to the power of quarter. And this definition basically gives you the idea the smallest scale, smallest diameter of your AD may occurs in your turbulent flow. You can think about this the smallest parcel. Okay. In general, when you look at the turbulent flow, when you have an AD means you group a certain amount of molecule together, and usually we can deal with the quantity or quality descriptions on the materials inside of the AD to say this is a homogeneous mixtures. Okay, then that means that in a turbulent flow, you can treat it for each of the AD that contains the homogeneous properties, and then you try to analyze it. Okay. Now, the chromograph scale, you can think about this as the minimal scale for the turbulent AD inside of a turbulent flow. And you can see there is the comparison between the size of the scale. In this case, in the first plot to tell you the eta is larger than the frame thickness. Okay, means the size of AD is larger than your frame thickness. Okay, and the third one, I want to tell you L, capital L represents the integral scale. Integral scale, you can treat it as the maximum AD you may have in your turbulent flow, which means for the case shown in this figure, tell you there is a different size of ADs exist in your turbulent flow, and the size range from the eta to the L, and those sizes are larger than the LH, the frame thickness. Okay, this is a basic comparison, give you the idea. The turbulent intensity inside your turbulent flow. Usually, when you have a large AD represent the turbulent intensity is relatively small. If you have a large amount of a small AD, that means the fluctuation become very strong, turbulent intensity increased. Okay. In the first case, we say this is so-called region 1. In the region 1, you can figure out the illustration on the comparison between these three scales, the frame thickness and the chromograph scale and the integral scale. And you can see in the first regions, you find out there is under a low intensity turbulence. All the AD has their own diameter larger than frame thickness. Okay, this is the first part you need to understand. I need to emphasize again here, the nu represent the kinematic viscosity, epsilon represent the dissipation rate of AD. Okay, and this is basically the definition you can refer to some textbooks on turbulent flow. Okay, in this case, since the older AD has larger diameter compared with the frame thickness, the inference coming from the AD, actually when the frame experience these big ADs, those AD, the motion or movement of AD will give you a wrinkling, or so-called the frame shape will be curved. Okay, like this way, this is the curved frame. And usually for premixed frame, you still can think about the frame thickness separate the fresh mixture zone from the bonded gas. Fresh mixture coming from the left-hand side, we understand this is the upstream side. After burning, then all the reactants be consumed, and they go to the downstream side in the right-hand side. That is the bonded gas. Okay. This is the first appearance to tell you the inference coming from the ADs in the turbulent flow. And here they tell you there is three important conclusions. The first one, the ADs do not roughen the frame front, which retains a smooth laminar appearance. They just give you the frame shape become a curve, a wrinkling, something like that. In this case, when you do the measurement on the frame speed, here we define the frame speed for the turbulent case as T divided by the frame speed of a laminar frame, and this ratio represents there is some important characteristics to tell us the inference coming from the turbulent intensity, and from the experiment they find St divided by SL, the ratio of the frame speed between the turbulent and the laminar is linear proportion to the integral scale divided by the frame thickness. And you can see the figures in the right-hand side. We plot the ratio of frame speed between the turbulence and the laminar, and against with the scale of integral scale and the frame thickness. For the low fluctuation, low intensity turbulence, this corner, you can see this corner here. You can see the ST divided by SL is almost a linear proportion to L divided by LH for 0.6 and 1.4. 0.6 and 1.4 is equal to the U prime divided by SL. U prime represents the velocity fluctuation in your turbulent flow. Okay. In this case, you will find out the region 1, as we described earlier in this the first set of figure. They show you the velocity fluctuation divided by frame speed is smaller than 2, and you find out actually the smallest scale, Kolmogorov scale, larger than the frame thickness. The only way they can give you the change on your frame structure just make the frame has a curvature, as shown here. Okay, and you find out the frame speed can be described by this equation. Okay, this equation simply tell you the ratio of frame speed between the turbulent and the laminar is linear proportion to the scale comparison between integral scale and frame thickness. Okay, and this equation tell you there these two ratio has a linear relationship. Okay, now you try to increase your velocity fluctuation U prime as much as possible. You find out when you increase to a certain value, when the scale, the Kolmogorov scale, the minimal diameter of AD is reached and equal to your frame thickness. Okay, and you find out the frame wrinkling, the curvature of the frame to achieve the maximum value. which means eta equal to LH will give you a possibility to reach a maximal wrinkling of the frame. Okay, this is a region 1, and eta equal to LH is the limit conditions for the region 1. Okay, this is the part 1. We are looking at the burning intensity or flame speeds under the low intensity turbulence. Now, if you increase the turbulent intensity more, here that means that we will increase the U prime divided by SL larger than 1.4. When you reach to the 2, when they equal to 2, U prime divided by SL equal to 2. Now we go to the region 2. For the region 2, you find out actually there is a certain amount of AD with the size smaller than the frame thickness. Okay, you can see there is for the region 1, you can see from the eta to L represent that there is a different size of AD exists in your turbulent flow, right? You have a larger AD, you have a small AD, but all sides should larger than the frame thickness. But for the region 2, there is some parts of ADs has a small AD size compared with the frame thickness. Okay, here there is a portion of small ADs and their size is smaller than the LH. Then what happened? You will see the frame still wrinkling. Okay, because they will be wrinkled by the ADs larger than the frame thickness. Okay, this part from LH to L in these regions, the scale of your turbulent AD is large enough, then they just give you the wrinkling or curvature on the frame shape. But for the small ADs with the size smaller than the frame thickness, they have a strong possibility to penetrate into your frame. Okay, and this is the happen. This is the appearance of the small AD penetrate into your frame thickness, and you find out those kinds of small ADs penetrate into the frame zones. Then they will enlarge the frame thickness, right? And you can have this very important influence, which means the area of interface between the combustion products and the fraction mixtures is significantly increased. Why? Those AD may come from the upstream side or from the downstream side. You can figure out from the upstream side, you can have a small AD bring fresh mixture and penetrate into the frame zones. And the same thing, if you have AD coming from the product side, they will bring the products with the high temperature, then penetrate into the frame thickness. Then they can have a chance to mitigate, which means those kinds of small ADs, they mitigate, they increase the interface, and these kinds of connections between the combustion products and the fraction mixtures will give you the strong interactions and promote the overall chemical reactions. Okay. Here I tell you the area interface between the combustion products and the fraction mixtures is significantly increased by the ADs and trend between the inner and outer boundary of the frame zone, which means from the upstream, from the downstream side, then they go to the frame zones, and this by this kinds of entrainment or penetration into the frame thickness, the frame thickness will be increased. Okay. And you can see from this scale comparison, you can see LH increase because you have a lot of small AT penetrate into the frame zone, then they enlarge the average frame thickness. Okay, in this critical case, when your fluctuation is just double of your nominal frame speed, you find out. And from the experiment, they find out the turbulent frame speed is just equal to 2 times velocity fluctuation. By these two relations, you figure out the ratio of frame speed between turbulent and nominal is just equal to 4. Okay, this is a typical value you should notice. Here you can see from the plot here. Okay, this plot tells you when you change the integral scale divided by OH, okay, you find out this is the horizontal line represents when you have a velocity fluctuation, U prime divided by SL equal to 2, the frame speed ratio is equal to 4. Okay, this is the critical frame speed ratio between turbulence and the laminar. And we change the structures from the low turbulent intensity to the large turbulent intensity when you have a velocity fluctuation ratio larger than 2. Okay, the region 2 tell you this is a very critical situation. Now the small particles, small eddies penetrate into the frame thickness, frame zones to broaden your frame thickness. Okay. Originally, you have a linear relationship between the frame speed ratio and the scale ratio, right? This is a linear relationship. Then you go to the velocity fluctuation to put to the non-dimensional velocity fluctuation by 2. Then this line becomes a horizontal line, represent a constant frame speed ratio. Then you further increase your velocity fluctuation larger than 2, then the curve shown in these figures to give you the so-called hyperbolic curve, right? This is a complete difference with the previous linear variation for lower turbulent intensity. Okay, now we go to the turbulent, the region 3. In the region 3, here we mentioned the velocity fluctuation is larger than 2, okay, and now your frame speed is inverse proportion to the length scale, okay. Now this is a hyperbolic line, is inverse proportion to scale. And what can we see from these figures and also these plots? The conclusion can be made by three important points. The first one, an increase in turbulent intensity is normally accompanied by a decrease in scale. Okay, decrease in scale means there is much of the eddies has a smaller size compared with the frame thickness, and most of the eddies can have a strong possibility to penetrate into your frame zone, your reaction zones, which means the curvature of your frame become less clear. They just do have a small change only without a large wrinkling occur on the frame surface. Okay, they tell you at very high levels of turbulence, the AD are too small to produce any noticeable wrinkling of the frame surface. In reality, those small eddies penetrate into your reaction zones. Okay, and to give you the structure like these figures, okay, shown in the plots, okay, and they mention here high burning rate are achieved. Okay, you can see the frame speed ratio increase to the upper side or right hand side. Okay, the curve increase to the high velocity, high frame speed ratio regions. They say this is due to the very large total area of frame surface created at the interface between the multitudinous small eddies and the combustion products in which they are enveloped. That means that when you have a lot of small eddies, including the eddy coming from the upstream side has some fresh mixtures, and the eddies from the downstream side has a product, then they penetrate into the reaction zone, the frame zones. They can broaden the frame thickness, and also they will increase very large total area of the frame surface, and they can interact each other. For products, they can preheat the preheating. They can preheat the AD coming from the upstream, including the fuel and the air or the mixing of the mixtures, and those kinds of integration will increase your burning intensity. Okay, and you can see from by the figure in the left-hand side, you can see you try to increase the turbulent intensity, the flame shape will start to change from the curvature, the wrinkling of the flame, and the wrinkling will reach to the maximum curvature. Then when you go to a continuous increase the turbulent intensities, then small eddies penetrate into the flame, the wrinkling become weakened, and will be weakened, and the flame becomes has some rotten surface occurs. This is the appearance. You can see the change of appearance by increasing the turbulent intensity, and the flame speed will change from the values, the linear relationship for low intensity turbulence to the hyperbolic inverse proportion relationship for the large scale large intensity turbulence. Okay. Now we go back to our slides to show you there is a very interesting pictures to let you know the flame appearance for the different kinds of turbulent intensity. Okay, here I think you can see. Okay, here this is a typical case. Okay, this figure is shown in 1.33a page in your lecture slides. The upper figures represent the turbulent burning flames with the shadow graph. Okay, observations, and you can see the U prime is equal to 3.1 meter per second. Is a lower burning intensity. Then you can see that there is some wrinkling, right? And the flame has some curvature flame, and with different kinds of curvature that mix together. And you can see there is those kinds of wrinkling or curvatures basically influenced by the larger size of the turbulent AD. But when you increase your fluctuation, velocity fluctuation up to 30.5 meter per second, is very strong turbulent intensity, then flame shape change becomes roughened. Okay, they do not have a smooth, small curve, curvature flame surface. And this is a typical comparison to let you know the flame surface change by the increase in the turbulent intensity from the small to the large turbulent intensity. Then flame shape change from the wrinkling flame to the roughened flame surface. Okay. Now, I think this is the end for the introductions on the combustion characteristic for premixed flame burning. The next step, we will go to look at the combustion characteristic of diffusion burning.